Hey, Laura, we're live right now. So what I would suggest, thanks for signing in. Yeah. What I suggest is let's sign out. We usually start about 7:35 to give people a little time to sign in. So 7:35, I'm going to give a little spiel introducing everything, and then I'll do an introduction to you, and then you're just going to take it away. Awesome. Thanks. And you can mute your video and all that, because otherwise you're going to be on YouTube. All right, well, good evening, everyone. Welcome. I'm glad you could attend. You are tuned in to Boise State Physics First Friday Astronomy event. My name is Brian Jackson. I'm a professor in the physics department here at Boise State University. If this is your first time joining us for one of these events, welcome. Usually, of course, we hold these in person, but since COVID, we've been having these virtually. In any case, they're still really fascinating. We've got a lot of really great speakers lined up for you. The way these events work is on the first Friday of every month, we bring in a guest to come in and speak about their space science work. Some of these guests are professional astronomers, as you'll hear tonight, but we've had other folks who come in from space science policy. We've had folks who teach space science. So we have a really wide variety of folks who do all kinds of space science. These events always take place on the first Friday of every month, whether or not school is in session. So we do these all through the summer, all through the winter. Even if Boise State is not holding class, these events still take place. They happen at 7:30 on that first Friday. And so today is the first Friday of October. So here we are. We have several events lined up for this fall that I want to show you a little bit about. Give me 1 second here. Yeah, so we have a great lineup for this fall. Tonight, you're going to hear from Dr. Laura Mayorga. The next event coming up in November will be from a presentation by Professor Barbara Ryden of Ohio State University. She's going to tell us about time travel. That should be really interesting. I'm not sure what she's going to talk about, but it'll be fascinating, I'm sure. And then in December, for the last event of the fall season, we're going to have Dr. Kathy Olkin, who works on NASA's Lucy mission to visit several asteroids. So those should be really fascinating talks coming up. All the talks are live streamed over YouTube and recorded. So if you have a friend or a family member or somebody who would like to see the talk but didn't manage to tune in, they're posted online on YouTube. You can go check out our website. My website is astrojack.com, so you can see the links to the recorded talks there if you missed them. We are set up so that you can ask questions of our speaker. If you're interested in asking questions of our speaker, let me show you how that works. Some of you may be viewing this from YouTube right now. Others of you may be viewing it from my website, astrojack.com. So let me show you how to get to where you can ask questions from the astrojack.com website. Okay, so here you can see the website and you can see the live stream here. It's a little bit delayed, you'll notice. If you click on the link here on the website, on astrojack.com, it'll take you to YouTube. And you'll see over here on the right-hand side of the window, this is the chat window. And so if you have questions you want to ask our speaker after her talk, you're welcome to type them into the chat window here. I think Google requires that you're logged in. But other than that, you can just chat questions. And then the way that we do these questions for the virtual presentations is I keep track of the chat window, and then I relay the questions to the speaker at the end of the presentation. Okay, and with that, let me introduce tonight's speaker. Our speaker tonight is Dr. Laura Mayorga. Dr. Mayorga is currently a postdoctoral fellow at the Johns Hopkins University Applied Physics Lab in Maryland. This is actually the home of the Dragonfly mission, those of you who are familiar with the NASA's Dragonfly mission. Before that, Dr. Mayorga was a postdoctoral fellow, a Harvard Future Faculty Leader Fellow, in fact, at the Harvard Center for Astrophysics in Cambridge. She earned her PhD and master's degree in astronomy from the New Mexico State University. And before that, she was an undergraduate at University of Washington, where she earned a degree in astronomy and physics. She's going to regale us tonight with some really fascinating science about exoplanets and about our own solar system and how we can make those two things talk to each other. And with that, I'm going to turn it over to Dr. Mayorga.
Thank you for that introduction. I'm going to share my screen. Let's see here. It's thinking. There's a security thing. 1 sec.
Oh, okay. Give her a second. As Those of you who are spending a lot of time on Zoom nowadays, you know that Zoom has these little eccentricities.
All right, this time with feeling.
I gotta make you a co-host again.
Sorry.
No, no problem.
I've had lots of computer troubles today, so I appreciate your guys' patience. All right, can we see my screen? Excellent. So as Brian said, my name is Laura Mayorga, and I have just moved to the Johns Hopkins University Applied Physics Lab. And what my research pertains to, I'm an exoplanet astronomer, but everything we know about exoplanets and what planets are like is what we've learned here on Earth and here with the exoplanets that are in our own backyard. So that being the solar system and everything in it. So what I want to talk to you guys today is about how we can use the solar system as our laboratory for studying other exoplanets, how they work, terrestrial gas giants, other asteroids, belts, and everything like that. All of that has to start here in what we have in the solar system as a test bed. So let's see. Can you guys see advancing? Did the slide advance? Yes.
You got it. Yep.
Excellent. Great. So what I'm showing you here on this slide is sort of the growth of the exoplanet field with time. As some of you may know, may be aware of, is that the field of exoplanets has grown rapidly from the discovery of the first exoplanet. The first exoplanet was actually found around a pulsar in 1992. And from this sort of strange thing that pulsars do, it's this sort of like dead star. They spin really fast, and because of the orientation of their magnetic fields, they send sort of these like pulses. And from the timing of those pulses, they were able to say something about an object being around it. And so those were actually, they now have names. They were named by the IAU. And they're, as you can see here. This particular system got to be named by Switzerland, and so they chose these three names for those three exoplanets around this pulsar, which has this very wonderful name of PSR B1257 plus 12, which really is a coordinate system here. That's how we named it originally, this pulsar. Now, the first sort of exoplanet that was sort of considered more colloquially and for which the Nobel Prize was recently awarded was around 51 Pegasi. This is 51 Pegasi B. This was found in 1995, and it got to be named by Italy, and so they called it Dimidium. Now, since then, we have used a variety of sort of equally clever ways to discover, at this point, over 4,100 exoplanets. These are confirmed exoplanets, but there are many more candidates in the pipeline. For example, the Transiting Exoplanet Survey Satellite has about another 2,000 candidates in the pipeline waiting to be confirmed. So in this chart, what I'm showing you is sort of the cumulative number of exoplanet detections as a function of the discovery year and broken down by the method used to discover it. So this is actually out of date as it was back in June, and we've definitely discovered more planets since then. Now, each of the techniques here have their own trials and tribulations. And it's only been in concert using multiple techniques that we've really started to understand more about what exoplanets are like. Now, the search for exoplanets has really been about finding a needle in a haystack, or as has been the strategy for surveys like the Kepler Space Telescope, it's about looking at a lot of haystacks to be able to find some needles. So the majority of the planets that have been discovered today have been with the transit and rate of velocity methods because of their unique ability to sort of look at many haystacks at once and with great precision. So here is the latest diagram of the exoplanets that we found so far as a function of their mass in Jupiter masses and their orbital periods, so basically how long their year is. And so you can see here that the kinds of planets we have discovered are sort of biased into certain regions of this diagram. Because of the way the methods work, like for example, the transit method, it relies on a transit actually occurring. So that transit occurs on a frequency of the planet's of the planet's year, or that orbital period. And so if you have a really short orbital period, you can observe many transits and you can prove to yourself that that planet is actually there. If it only transit once, you'll never know exactly what it was that that object was, or perhaps it has a really long period. And so you need a really, really long time to observe it. And so because of this, most of the transits that we have found, or most of the planets that we observed and discovered with the transit method, which is currently 76% of the population, ends up being very large objects, radially large. So they are very obvious when they cross in front of their stars, and on very short orbits so that we see them do this many times. And so you can see that generally the transit and radial velocity discovered planets dominate the sample, but microlensing is another such method we've used to discover several planets. You can see here there are the triangles on this plot. And the Nancy Roman Space Telescope is actually going to have a microlensing survey on it. So the way microlensing works is through gravitational lensing, where gravity actually bends the light that's passing around some sort of massive object, you can see a lot fainter things that are behind them and being lensed. And so if you happen to have a planet transit, while the star it's around is also being lensed, you can detect that where you wouldn't normally. And so the Nancy Roman Space Telescope is hoping to discover many planets using this technique. There's also several that we've discovered so far with imaging. So this is direct imaging, where instead of using some sort of proxy like these other methods used to determine that the planet is actually present, you can actually see the light from the star and the planet separately in an observation. For now, this has been done from the ground mainly in sort of near infrared wavelengths. So we found some very young, hot objects, sort of newly formed objects around some interesting stars. And so that has sort of made up another small percent of the sample. And then all these other sort of techniques make up just 1% of the currently known population. So we'll see what happens there with new instrumentation and new technologies come online. But what we want to understand is not just how many planets there are and what sort of these fundamental properties they have, but we want to understand is what are the atmospheres of these planets like? What's their climate? What processes have been at play to sculpt them, whether they have surfaces or are they gas giants? And this is a particularly good time to be in exoplanets because the instruments that we are using and developing are getting so precise that we are finally starting to find planets like those that are in our own solar system. So for many people in this field, what drives them is the search for another Earth or the search for life. And so it's really not just about finding needles in haystacks, it's about finding the right kind of needle and figuring out how is it that we reach Earths. And so as I mentioned earlier, let's see if this plays. No, I had the same problem earlier. So the way the rate of velocity technique works, well, actually, maybe I see if I can actually, no, I'm not gonna try. Not while I'm giving a talk, not through this. The way the rate of velocity method works is you can observe the spectral lines of a star. So a star, over all the colors of the rainbow, there are sort of dark, at certain wavelengths, the star is darker because of absorption of a particular molecule in its atmosphere, or an atom or some sort of some particle or constituent is blocking that light. Because of the planet orbiting around it, they have to both orbit the center of mass of the system. And so what ends up happening is because they're both in motion, there's a small redshift and blue shift of the light we get from that star. And so what ends up happening is that as a planet orbits its star, the star's lines appear to move. And from how much those lines move, we can say something about how massive that planet is relative to the host star. If you do this for very if you are very, very precise and have a very high spectral resolution where you can split apart those lines and have detect smaller shifts, you can detect smaller mass planets. Now, with the way the transit technique works is that you are observing a star. You don't see the star. You can't see a disk like this. You're basically just measuring some amount of flux, some amount of brightness from the star. Now, every time a planet transits in front of it, you get a dip in the light from that star. You don't see the planet, you just see that it's casting a shadow on that star. Now, in reality, what's happening is that because these very short period planets are tightly locked to their host stars, and so the same face is always facing that star, there is a permanent day side and this permanent night side. Now, it turns out that if that planet is large enough or close enough or hot enough, you can see light from the planet in addition to the light you see from the star. And so when the planet crosses behind the star, you get another dip because that's what's the light from the planet that is now missing because the star is blocking it. And so the neat thing about measuring the entire orbital period like this is you can get a phase curve, either in emitted light, so this thermal light, or in reflected light from the planet. And so here you can see again, it's about to eclipse behind the star, and that baseline level here is just the star alone. So this entire variation here is caused by light that is coming from the planet. And we'll be in thermal, we are able to say something about how the temperature of the day side varies against the temperature of the night side. Now for reflected light, this shape of this curve is now dependent on atmospheric properties, what particles are in the atmosphere, whether they're gas or some sort of cloud or haze, that will change this shape and of course its amplitude. So since these are very short period planets that we've discovered so far, typically, these planets are, these signals can be very large depending on how hot they are or how large these planets are. But as we move forward, these signals can be very small. And so Kepler, for example, during its nominal mission, was able to achieve precisions for the variations it could measure down to a few parts per million to make these kind of phase curves measurements. The other benefit of doing transmission spectroscopy or of doing transit method observations is you can do this thing called transmission spectroscopy, where as the planet transits, depending on what wavelength you're looking at, different particles in the atmosphere are blocking various amounts of that light coming through. So in this case, on this diagram on the right here, this little movie is showing how a planet's atmosphere becomes more or less opaque depending on the wavelength. So in this case, we're looking at a model of water vapor. So this is a water band, for example. And as you track through the various wavelengths here, you can see that the planet blocks more light as we pass through the water band. And we've managed to do this for several planets. Here you can see just about a dozen or so. And so we've been able to start to say something more statistical or an ensemble sense about what elements are in exoplanet atmospheres. So like here we have sodium and potassium, and then water. And start to understand what are causing these differences. Are they clouds or hazes, which can sort of truncate the height of the various features in an exoplanet atmosphere, or what else might be going on? So this technique is predominantly used the Hubble Space Telescope and other sort of single transit telescopes with good stability and high precision photometry or low resolution spectroscopy. So to do that kind of work, though, requires a lot of time and resources. So these two techniques that I've mentioned, to build up the requisite signal to say something about that planet's atmosphere, requires observing multiple transits. So here is a table of some of the best terrestrial targets that have been identified, and the simulated number of transits required to measure a Venus-like atmosphere on them with the James Webb Space Telescope. So here we see some of these planets with the TRAPPIST system, which is around an M dwarf star. And these are also M dwarf host stars. And so you can see here that depending on whether you're looking at in emission for that secondary eclipse or the transmission that we were talking about, the number of transits you have to observe is very different. And these number of transits, of course, are spaced out by how long the year is on that planet. So if the period of an Earth-like planet is 300 days, or maybe it's around M star and less, we're still looking at many observations in order to detect features in a planet's atmosphere. So beyond just being able to understand their atmospheres, we want to understand many atmospheres, right? We want to characterize not just their masses and radii, but what the atmospheres are like for a large number of exoplanets so that we can understand how it is that they form, how it is that they evolve, and the physics and chemistry of the planetary environment. So the technique that I favor and that we can definitely use the source to prepare for is direct imaging, as I mentioned earlier. So one of the recommendations from the National Academy's Exoplanet Science Strategy Report, of whose front cover page I show here, is a direct imaging mission to measure the reflected light, is to have a direct imaging mission to measure the reflected light of an exo-Earth. So here on the left, you can see the finding that direct imaging is the only path currently identified, and that we should do a large strategic direct imaging mission. So with this powerful technique where we are observing the light from the planet directly, rather than entangled with stellar light, this is how we first began looking at the bodies in our solar system. So there's a number of ground-based direct imaging instruments right now, but we're hoping to fly several as well. And so here is a chart of the 4 astrophysics decadal concept missions. So every 10 years, the astronomy community sort of gets together and tries to decide, what does the field need next? What are we working on next? What are sort of the big questions that we're trying to answer? So out of a decadal survey like this, that's how James Webb was decided to go forth. That's how Hubble came about. And these are the 4 contenders for the next set. Nancy Roman also came from one of these as well. So Nancy Roman is actually really important for direct imaging because it has a coronagraph on board that is a technical demonstration that you can fly a coronagraph, because we always have to test everything before we actually do it. And so of these 4 concepts, the middle 2, LUVOIR and HABEX, are both equipped with either a coronagraph or a star shade with which they may be able to do, if they're selected, direct imaging studies. So the way direct imaging works, it's a completely different beast from transit and radial velocity surveys, but it's a particularly powerful technique where we are observing the light from the planet directly. And so here's a simulated image of our own solar system as if it were at 15 parsecs. And so in the middle here, this is where the coronagraph is occulting the light from the host star. So basically there's just a little, in the case of a coronagraph, an actual like little plate in the front of the telescope that is blocking light. So because of how wide that little plate is and how far away the system is, we will not see Mercury from this sort of perspective. We barely see Venus. It's on the edge here. You probably wouldn't find it in the noise. We see Earth. We don't see Mars because Mars is too small. We see Jupiter, and then we don't see Saturn or any of the other gas giants because they are outside of the field of view of our telescope. And so there's a lot of work going in right now to how to make the planets stand out as much as possible in an image like this. So in order to have this be as dark as possible, there's a lot of technology right now technology development right now to try to make this dark hole as dark as possible. And then to be able to detect these planets, it comes down to how bright are they in comparison to their host star? What is that brightness ratio, which we call contrast? So firstly, because we're only seeing them from sort of a more polar perspective, or even if it was edge on, we will never see them transit or eclipse. Generally, you will never see planets fully illuminated in a direct imaging scenario, or in anywhere near fully illuminated. For this perspective, for example, Earth is only being half illuminated, right? Because the day side's over here, the night side's over here. So we're only seeing a phase angle of about 90 degrees. I have a diagram coming up to explain that, or to show that. So the question becomes, how bright is a planet compared to its host star? is that a detectable amount of brightness? And how sensitive do we need to be able to characterize that and say something about what its atmosphere or surface might be like? So here's a chart, for example, of the contrast, that brightness ratio of the planet to its host star as a function of its separation on sky. So this is an angular separation rather than a sort of physical or like or a semi-major axis. Up here, we're seeing a couple of the direct imaging planets that we've already discovered. And these are sort of the brightness thresholds of various different instruments that are capable of doing direct imaging. Down here are a couple of radio velocity planets that we already know about, but haven't been able to take direct imaging observations of them because they have much lower contrast ratios to their host stars. And you can see here, this is where all the planets in our solar system fall. So here's Jupiter at about 10 to the minus 9, and here's Earth at about 10 to the minus 10. So the question we're trying to answer is, when you see just a single dot, and if that dot is not labeled, it doesn't say, it's not screaming at you Jupiter, it's not screaming at you Earth, it's not saying anything, how do you figure out, is this an Earth-like planet? Or is this some sort of gas giant like Jupiter? And if you can classify it between these two, what more can you say about it? Can you say this one has a great red spot? Can you say it has banded clouds? Or can you say something about the continents versus ocean breakdown on a planet such as this? And so to do this, we need to understand how the reflectivity of a planet changes as a function of geometry. So this phase curve, which we were looking at before, is a measure of reflectivity as a function of that phase angle. The phase angle is the angle between the star, the planet, and you, the observer. So as light passes through an atmosphere or to a surface, it can take a complicated path to reflect back to us, scatter back to us. So we need to understand how these unresolved differences in atmospheric properties or on the surface can affect that from all observational perspectives, because we'll never know exactly how we're looking at a system. And so depending on the material you have, and so for example, I have this slide where we have 3 different spheres with different reflected properties. So here's a Lambertian. This is sort of an ideally diffusing sphere. The way it reflects light can be written with a simple equation. And this is sort of a perfect mirror, which we call specular reflection. So if you look in a mirror, that's specular. Now, if you look at a whiteboard, to us in the optical, it looks sort of like it's ideal diffuse, or maybe perhaps some sort of directional diffuse, but it looks pretty much all white. But if you looked at a whiteboard in, say, infrared wavelengths, it would almost look exactly like a mirror. And so the breakdown of what the surface is made out of, what those particle properties change as a function of not only wavelength, but how you're looking at it. So here's an example of Jupiter as it goes through various phases. So here at full, just like the moon, it's at 0 degrees phase angle. So we're all basically in a line. That angle is 0. Here it is half illuminated, like we were looking at it in that previous simulated image. So unlike a perfect surface, though, gas giants and anything with an atmosphere is a little bit more complicated, because rather than bouncing off that photon coming in and bouncing off of one singular surface, it can penetrate to another deeper layer in the atmosphere before it actually gets reflected back. So this phase curve, not only is it dependent on the particle properties, whatever is crossing in the way, is also probes something about the atmospheric structure, its composition and temperature as it goes all the way down. And of course, we're still trying to answer, how bright does a planet need to be to detect it with our instrumentation, and how bright is that planet, or how faint do we need to go in order to be able to detect it and characterize it? So of course, brighter planets are easier to detect. What we learned from studying Jupiter is that it's not a perfect Lambertian. It's not a perfect simple model. And everything we learn from Jupiter as giant planets these are all stepping stones and the first steps we take to try to understand terrestrial planets, because they are sort of easier since they are larger, more easier to detect. We have more of them that we know about, and so we can practice on them before we actually get to finding terrestrial planets. And so what I'm showing you here is the phase curve of Jupiter in 2 different wavelengths. This is basically optical blue, and this is a little bit redder than red, if you will. Not quite thermal, but very, very red. And what you're seeing here is how its brightness falls off as a function of this phase angle. Now, for direct imaging missions, we're mainly going to be observing something right here between 60 and 120 degrees, always sort of partially illuminated. And so you can see here, compared to sort of the ideal simplistic case, that Jupiter is fainter at almost all phase angles. It also has this very steep fall off. And this steep fall off is related to sort of large particles in Jupiter's atmosphere that cause a very large backscattering effect at these low phase angles. And so we don't actually know what those particles are in Jupiter's atmosphere, and we don't know if they are present on other exoplanets yet. Making the jump now to terrestrial planets, they're even more complicated than their gas giant older siblings because these unresolved surface features will also impact our signal. And so what I'm showing here on the left is a movie of the Earth, as we saw from the epoxy mission, which basically looked back at the Earth so we could see it as if it were an exoplanet. And as you watch it rotate, you can see with your own eyes that the brightness of the planet is changing, even if you can't disintegrate it with your own eyes. But this varies, you can see, based on the weather patterns, the continental patterns. You see how it seems to get darker as Australia comes into view, and it sort of looks very bright. You can see sort of a little hint of this ocean glint coming here from the Pacific Ocean. And so the Earth has actually been a really good exoplanet case for us because we've been able to model it and sort of understand the reflected light from it, so we can try to have a good handle on what an exo-Earth is going to look like. But it is not only important to understand what Earth looks like, we also need to know what other sort of terrestrial objects look like, so we know what a not Earth looks like. And so I present to you the other exoplanets, terrestrial exoplanets in our backyard. And what I mean is the Galilean satellites of Jupiter. Now, I want to be clear, I'm not talking about exomoons. I'm saying that these are surfaces in our solar system, which are examples of surfaces that are able to happen on planetary objects the universe is able to create. And that despite how similar these four moons are in size, density, where they form, temperature, for example, they're all radically different and show a great variety and are just a sample of what the universe can create. So for example, Io is volcanically active, Ganymede has a magnetic field, and then for Europa is covered in ice and has a subsurface ocean. And then Callisto is sort of just has a really old surface that has been heavily cratered. And so using these, we can measure their reflectivities as a function of rotation and their illumination, and figure out what they could potentially look like in a direct imaging observation. So to do this, we use data from the Cassini Imaging Science Subsystem. Now, Cassini, en route to Saturn, observed Jupiter during a flyby, what they call the Millennium Flyby, in late 2000 to early 2001. And during that time, the ISS took tens of thousands of images of Jupiter with these two cameras, most often in 6 filters. And I'll be showing you results from the flyby for the rest of this talk. So even though the main target of these observations was Jupiter, which you can see in these 2 example images, in the background, the moons basically snuck into these observations. Later, the moons were actually targeted on their own, but conveniently, they also showed up in all the Jupiter targeting images. So what I was able to do is find where all the moons were in these images, put down a little aperture around them, disintegrate the light, and then basically come up with an exoplanet analogous observation. So once you disintegrate all their light, you get a phase curve here. So here's the reflectivity of the moon Io in the green filter as a function of illumination or phase angle here. And we can compare this to that sort of simplistic model we saw earlier with Jupiter. That's this one here. And so we can already see that just like Jupiter, this one is much darker than that Lambertian simple model. And because I can resolve the moons, I know exactly what part of the moon is underneath an image at any point in time, even though just because I'm in the solar system and I have that information, I can split up the rotational variations, which are shown here, how the reflectivity varies as a function of the longitude on the object, and separate that from these illumination variations. So going back and forth, I can fit this and remove that from here and then disentangle them from each other. Those rotational variations, I can then assume that if my planet is an orange and each orange slice has a particular brightness, I can invert this curve, this rotational curve of reflectivity to make a brightness map. And so that's what's shown here. And then again, because I have the Galilean satellites actually resolved in observations, I can compare that to actual maps and see how well we're actually doing. Now, the issue is that this is a measure of reflectivity. The map isn't necessarily a measure of reflectivity. It has some sort of reflectivity information in it, but because of the way it had to be constructed, it's blended a little bit. So that they took all these images from the Galileo and Voyager satellites and sort of adjusted the contrast and brightness to sort of get a sort of smooth, cohesive map. So they're not quite the same. But we can compare them and see how well this technique is actually doing at recovering the surface and color variations. And then if we were to increase the size of the Galilean satellites, we can say, what does it look like if it were an Earth-sized exoplanet around a sun-like star at 1 AU? And so here's the phase curves of all 4 of the Galilean satellites, just to sort of summarize the results we got. And you can see here the expected contrast ratio if they were an Earth-sized planet around a sun-like star at 1 AU. So here's for all 4. This main line here in the middle is the phase angle, is the actual phase curve. And sort of this shaded region around it is those rotational variations, what the variation they could cause as the object rotates. And again, I'm just showing you all of the Lambertian models, those simplistic ideal diffuse spheres. And so you can see again, just like Jupiter, there's this steep opposition effect. In fact, these are even steeper than what we saw with Jupiter. So even though there's no big particle that's doing backscattering in the atmosphere, this is something that's on the surface and something to do with the geology and the particles, the size of the particles on the surface. And they are much, much darker. So with Jupiter, this number of how much darker it was at 60 degrees is about 25%. Here, we're talking about 50%. So they are much, much darker if we were just going to assume that they were an ideal diffuse sphere. And so for that case of trying to detect it with a direct imaging, even though you'd say, oh, they're actually pretty bright when they're full, we won't be looking at them full. We'll be looking at this sort of half illuminated, and you can see that they are much, much fainter. And this is just to detect it. For those rotational variations, they get even fainter, or will need even fainter. So we did this in all 5 of the filters. The 6th was blue, which I sort of showed you earlier for the Jupiter data. But for this data, we didn't have enough at low phase angles to make this, to get a rotational curve for all of them. And we can get all of our little maps here, and you can see how the rotational variations in reflectivity vary depending on the wavelength that you're looking at. So being able to make multi-wavelength observations is going to be really important for being able to characterize these surfaces. And what's really cool is that now we want to be able to put this information together and say something about what are the actual regional differences in this case, on the moon, but eventually on the exoplanets. And so here I'm showing you just sort of the, if this is a false color map made up of sort of 3 near sort of visual colors that we can see, here's sort of the best or the closest match that I have from the data set here. And you can sort of start to say, like, depending on what longitude I was looking at that was sort of centered in my observation, maybe I can say, oh, they're all sort of really bright here. So if all of them are, or if all three wavelengths are really bright, that means it's probably pretty white. And maybe I'm looking at this region right here. Or maybe if over here it's really bright in a certain wavelength over a different wavelength, maybe I can tell that all the region around Pele, this volcano here, is orange. That's the kind of connections we want to be able to make from these data sets. Here, from where it's a simple speck of light, and I can't say anything about what side of the exoplanet I'm looking at, to be able to say something about a little speck of light to say something about the map and what that surface is like. Skip ahead here. So if you remember though, the image we were looking at of the solar system was basically completely face on. So face on, just like it is in this image of HR 8799 and of its 4 exoplanets. So what we're looking at is down at the poles of these planets, rather than edge on, which is how we're used to seeing everything in the solar system because we are in the plane and we tend to send out missions and satellites in the plane as well. So we're always looking from the equator. But what we know just from looking around in our solar system is that the poles of our planets don't always look the same as they do on the equator. So Earth, for example, is 2 polar ice caps. Here's Mars. Mars's ice caps change depending on the season. Here's Saturn. You can see that the cloud patterns cause a very different appearance on the North Pole. To say nothing of Uranus, which is completely rolling on its side. So if we were expecting to see a pole of a planet and we see an equator, how are we going to know those differences? And so sort of just to make my point here is my cat, who on her upper side is one color and who on her belly is a completely different color. So depending on the angle and orientation of my cat, I expect to see different colors. So what angles and orientations do we actually need? So here I'm going to sort of lay out what inclination we need to observe our planet at, or the latitude from which we will be observing it from, and the phase angle we'll need to observe it from. So in this sort of orientation, 0 is edge on, so we're seeing it from the equator, where 90 and -90 are face on, so we're seeing it from the pole. Now for direct imaging, like I said, you're never going to see it transit. You'll never see it eclipse. So you're never going to see anything near 0 or near 180 degrees because that is blocked by the occulting mechanism. Additionally, everything sort of beyond 120, as we saw earlier, starts to get really, really faint. So here they'll be too faint to detect and we'll probably never see that. Also, it's really hard to look at systems that are edge on because even in our own solar system, we have the asteroid belt, we have the Kuiper belt, there's these debris disks and dust that could be in the way. And trying to detect planets through that could potentially be difficult. So looking at them from the equator could potentially be difficult. We might not even detect any for exoplanets. Now, this is exactly where we have observed exoplanets in our own backyard, right? This is where all my Cassini data is from the equatorial view. And so what we need to do is we need to measure inclinations and phase angles of all the planets in our solar system in regions like this. One such mission that can potentially provide data from that is the Juno mission. So Juno went to Jupiter and is in this highly inclined orbit. And with JunoCam, we've been getting such wonderful images, such as this here on the right, which is Jupiter half illuminated from the South Pole in this case. And you can see already that there's a hint for Jupiter, especially, as we saw earlier in the couple images ago, or a couple slides ago, that the poles are going to be a very different beast than looking at it from the equator. Also, one of the images or one of the missions that I am on that is proposed for the planetary decadal that's coming up is the Io Volcano Observer, or IVO. And what its goal is to fly around Io, map Io, and try to understand or how its core is laid out. There's a couple different scenarios for how its volcanic activity can be sustained. We basically want to follow the heat and understand how Io's what runs the volcanoes, what's its sort of what are the internal sort of components and how does it work. But while we're doing that, since we're in such a long orbit, one of the things I'm trying to do is figure out how we could possibly observe Jupiter from these higher vantage points as if it were an exoplanet and fill out that parameter space that we were discussing earlier. So my last slide I want to leave you with is this diagram from the XKCD comic, if you're familiar with it. While there are many things in our solar system that we wish we had, for example, hot Jupiters, these planets much, much closer than Mercury's orbit, for example, and super Earths, which is sort of this weird object where we're not sure, are they rocky with very large atmospheric envelopes, or are they more like miniature Neptunes? What are they actually like? We don't have anything like that in our solar system. But we do have, despite all these changes we could potentially make to our solar system, we do have lots of objects in Jupiter, in the moons, in asteroids to try to understand sort of some of the weird pathways that we can have planets form and what they actually might be like. So with that, I'll go ahead and say thank you, and I'm happy to take questions.
Excellent. Thanks, Laura. That was awesome. Let's see. We have some questions here in the YouTube chat. Let me see. I'm trying to interpret what he's saying here. I think the question is about whether you could directly image the TRAPPIST system. What do you think about that? Do you think what are the prospects for directly imaging TRAPPIST?
Yeah. So if I remember correctly, the issue for M dwarfs, which makes them very good for transit method radial velocity surveys, is that because they're so small, their habitable zones move in, and you can have shorter period planets basically be potentially more Earth-like. But the issue with that is, as you move, let me see, if you move your planets sort of closer into the star, they are more likely to fall behind the occulting mechanism, right? Because this blocks an angular region on the sky. So if the TRAPPIST planet system were really, really close, closer than they are now, we might be able to see some of them sort of in the observable region out here. But they're actually too far away because they are so close to their host star that they would all fall directly behind an occulting mechanism from in a direct imaging telescope.
Yeah, I saw the question on YouTube, and I was just curious to know what the angular separation is for the outermost planet in TRAPPIST, and it's 20 nanoradians.
Oh gosh, I do it in arcseconds. What's an arcsecond?
Anyway, it's a fraction, right?
It's very, very close.
Very, very close. Even though they're 40 light years, only 40 light years away, the planets are all, it's really amazing to think TRAPPIST-1 planets are so close to the star, really close.
Yeah, they're very, very close.
Yeah. Oh, good. Okay, yeah, that was the question. Does anyone in the room here, anyone in the Zoom room have any questions for our speaker? I would be interested, could you bring back up your phase curve for the Galilean satellites?
Yeah.
The one where you were comparing where you had the sort of colored bands around, yeah, that one right there.
Mm-hmm.
Boy, it's so interesting to me that Io falls right in between some of the other moons. I would have thought, given that Io has a rocky surface and the other moons have these icy surfaces, that their phase curves would be very distinctive, but they're really not.
Yeah, that's a little bit surprising to me as well, that there's not some sort of like, I don't know, like a bump or some sort of variation of, but that would require like the entire surface to be doing sort of something, have some sort of directional scattering component. The one thing that I don't have is all of my data sort of stops short of sort of that like crescent phase, that 180 degrees just about, just because we need to avoid the sun when we make these kinds of observations. And there is evidence, for example, for like Titan, that this picks back up again at the end. So that there's some sort of particle in in Titan's atmosphere, perhaps that high altitude haze, that is really strongly forward scattering. And so that can cause variation there.
Yeah, and in fact, after your afternoon presentation, I got interested to look up. Oh, I'm going to stop your screen sharing. Is that okay? Is that okay?
Oh yeah, that's fine.
Oops, let's try that again. I got really interested in looking up the phase curve for Venus. So this is what I found on Wikipedia. I have no idea whether this is a real phase curve or not.
So it's an absolute magnitude, which is what makes it a little bit difficult to compare.
Yeah. But it does show, the Venus curve does show that sort of bump that you were just describing, of, I guess, which is the forward scattering from the cloud deck, huh?
Yeah, so the data we have from Cassini stops at about 160 degrees, because that is the sun avoidance angle. So the bump must be like the very edge of that bump, or perhaps it's even a little bit sooner on Titan. So some of the modeling I was doing, which I didn't show in this talk, for potentially reflective planets with like a TESS sort of instrument, so much redder wavelengths than like Kepler was showing that for some of these sort of like salt clouds, like Na2S clouds, you get an extra bump out here because there's like a from probing the particle properties themselves, which is what you're doing at those wavelengths. So for that particular case, in the optical, it's like you were sort of probing sort of the general, just like reflectivity of the entire planet. It wasn't, and you're probing more like Rayleigh scattering processes, whereas at longer wavelengths, you're really probing more about what the particles themselves, their actual. So if like you had one single particle and a phase curve for that one single particle, you were seeing that sort of more holistically show up, which is really interesting. So that's why having multiple wavelengths is important, not just getting one phase curve. It's about getting it in multiple wavelengths to see how that variation changes.
And have we seen evidence for that kind of forward scattering from any exoplanets? I guess I don't remember seeing any papers about showing evidence for that. I did see some theoretical calculations, but I don't know if I've seen any observational.
Yeah, the thing with exoplanets that is sort of very difficult is that we haven't really gotten to the precision that would be necessary to detect those kinds of effects. So for that, the theoretical work that I was doing, I was showing that like in TESS, the overall peak of that phase curve was like 30 parts per million, which is just about on the edge of the noise floor for TESS. But that little bump is like down at like 1 part per million. So these require really, really high precision observations.
So, I'm trying to think if any of the Kepler systems had 1 part per million. Because I mean, some of the odd Jupiters that we have from Kepler, they have like 1,000 transits.
Yeah, so Kepler is a lot bluer bandpass, even though it doesn't really like seem that way, but it's a lot bluer than TESS is, and so it's not really probing the particle properties the same way. And so if you look, you can literally you can look at the same planet at those two different band passes, and you can see it looks like a perfect sort of, not Lambertian, but almost like that same sinusoidal shape in the blue, and it's much brighter, like 150 parts per million at the peak, but the TESS curve is like 30, and then that little like 1 part per million I was talking about.
Interesting. One of the students here in the room has a question for you. Why don't you go ahead?
It was just a question about, is the point of trying to image Jupiter from those higher altitudes meant to give us more chances at trying to image Jupiter with like the tools or wavelengths, or is this like, I don't know if practice is the right word, but for like those planets that are farther outside and we don't get as much of a chance to get those more frequent like periods for observation?
Yeah, it's really more about.
Laura, let me get you to repeat your question, because I'm not sure the audio is coming through so well on the YouTube.
Oh, okay. So if I can just read it from the chat here, is that fine? So she was asking, is the point of trying to image Jupiter from these higher inclinations, from different angles, meant to give us more chances to try to image Jupiter with more tools and wavelengths, or is this basically kind of practice for because we don't have much opportunity to image planets further outside of our further out in our solar system? It's kind of like when you look at an exoplanet system, any exoplanet system, if you could see it with your telescopic eyes, regardless of what technique you're using, it is completely randomly oriented in space, right? There's no preferred orientation for an exoplanet system. So if you were to see a Jupiter, you have no idea where it is in its orbit, what's its illumination conditions. You don't know what side of it you're looking at. And so, for example, one idea was that you could use its color to figure out, is it more of a Jupiter, or is it more of like a Neptune, or what is it? But the issue with that is that Jupiter's color varies with phase angle. So depending on the illumination, it could try to masquerade as more of a Neptune, or it could confuse you as to what it actually is. And so looking at it from the poles, where that Juno data is suggesting that it might be bluer, is important because we need to understand from that direction, can Jupiter trick us and pretend it's something else as well? So it's sort of by trying to cover all our bases, when we get that exoplanet data, we can compare it to the sort of ground truth observations that we have in the solar system. So sort of just place it in context, right? Because if we just get a random observation and we don't know anything, we could be like, well, maybe it looks like Jupiter, maybe it doesn't, but we won't actually know unless we can actually do a comparison and basically check everything off that it could not be.
Yeah, really fascinating. Any other questions? Folks in the room, folks on YouTube? Well, I'm already getting a lot of rave reviews from the presentation. I just got an email from one of the folks who watched it and said it was great. So that was really excellent. Thanks so much.
Glad.
Yeah, really. And I know it's a little weird to give a talk like this where you're really only seeing one person, but I promise you got an audience out there and a lot of new fans. All right, so thanks for joining us, everyone. Again, the next one of these talks will be in November, first Friday, November. Excuse me. Yes, first Friday of November, November 6th. That'll be 7:30 p.m. and it'll be live streamed just like this. Everyone take care. Check in with your friends and family. These are crazy times. Take care of everybody. And we'll see you all later. And stick around for just 1 second, Laura, before we leave.